All right, now let's discuss some basic properties of cross products. This is not like I did with the dot product. This is not going to be a comprehensive cross product video. It's going to cover the basic properties of the cross product. It will have more properties than this, but I don't necessarily want you thinking about these right now. So this is a basic properties video. Maybe in the future I'll publish a um, you know advanced properties or more properties video, but for the beginning, for an introduction to the cross products, this should be enough to get you going. I also have a separate video previously that shows you how to calculate this determinant right here, which is this definition. So you can go there and check that out if you're not very familiar or if you forgot how to do this. Just as a quick reminder, I just recorded that one and I made a mistake in the first example. So but I go over it again. I correct it in the video. You can keep an eye out for it if you're watching this first. All right. So here are some important properties. I'm not going to be proving these. I just want to tell you them. There are three basic properties that I want you to know. First of all, the cross product U cross V is perpendicular to both U and V. It's a vector, right? So this is the cross product, so it's a vector, and it's perpendicular to both. So geometrically, that means it looks a little bit like we have vector U, vector V like this, and the cross product is upward, or maybe downward, right? I'll show you the next property later. But U cross V is perpendicular to both. And this is why this is only possible to do in dimension 3 or higher, because well, you have this third direction to go towards. If you're in the plane, there will be no upward for you to go, right? If you're in dimension higher, things are a little bit more complicated. I'm not going to bother talking about this in this video. So if you look at example 18 there, we're asked to find a vector that's perpendicular to both j minus k and I plus j. That is the cross product of these two. So I'll say that my vector u is j minus k. So that is the vector 0, 1, minus 1. And my vector v is I plus j. So that is vector 1, 1, 0. Again, these are the standard basis vectors. So I is 1, 0, 0. J is 0, 1, 0. And k is 0, 0, 1. So by plugging those in, I do get these two vectors that I have there. And to find a vector that's perpendicular to both, I just do the cross products of these two. U cross V will be, bring it out. I goes here, J goes second, K goes third, put the coordinates of U, 0, 1, negative 1, 1, 1, 0, and then just have fun with finding this determinant. I'll do it. But before I do that, pay attention to the order. U goes first row, second row, right, before V, which is third row. This matters here. The order in which you plug these in does matter. If you change the order, you get a negative sign in your answer, and that matters, especially for calculus when you're calculating areas, volumes, and such. So I'll do by this determinant by row expansion or minor determinant decomposition. So this will be I times the determinant of 1, negative 1, 1, 0, minus j, this minus from the formula. Delete the correct rows, 0, negative 1, 1, 0, plus k, expanding the third. So again, delete this, right? Get 0, 1, 1, 1. And let me double check that I'm deleting things correctly. It seems like I am. So this is I times minus 1, right? 0. Minus j times minus 1 again. And plus k times minus 1. So this will be I. So it's 3 minuses there, so minus j. And then minus k. And so that will be the vector 1, negative 1. 1. So that is the answer to the problem. If you really want to be picky about it, you can double check. If you call this W, I guess, what's W dot product? U, right? That would be 1 times 0, 0, plus negative 1 times 1, so negative 1, and then 1 times negative 1, so negative 1, it should be 0. What have I done wrong? Yep, I see it. You saw it first. K is negative K right here. You see that? So, good idea to double check your work like I'm doing with mine. Now and then. Getting tired. So that is the correct answer to the problem. And then that third element will be negative 1 times negative 1, which is plus 1. And then now that will be 0, which shows you that V and U are W and U are perpendicular. If you do W and V, you will also get, what will you get? 1 times 1 is 1, negative 1 times 1 is negative 1, and then plus 0, you also get 0. So this is a vector that's perpendicular to both. It's not the only one, right? This is why the problem asks for a vector that's perpendicular to both. It's not the only one, and that leads me to the second property, because this one is also perpendicular to both, just pointing the opposite way, right? But the second property is that the cross product follows the right-hand rule, right? Meaning, if you have U right here, V right here, again, you can, in this order, right, point your thumb towards this thing, right? And then if you do things that way, right hand, thumb towards the grain vector, and then index finger towards U, and then you can curl from U to V, or have your middle finger point that way. So if this is your thumb, this is your index, you can curl your index fingers to the inside, to the palm of your hand towards V. So that will follow the right hand rule. So V is the correct decision for U cross V. So the grain one actually is the correct decision. This bottom one will be the incorrect one for the cross products, okay? This is the second property. Mostly graphically helps you and helps you understand more or less how things are supposed to be. And third, we have this more interesting property, which says that the magnitude of the cross product is the area of the parallelogram determined by these two vectors. So if you have U here and V here, you can copy this thing, it's not what I wanted, put it here, right? Copy this other one, put it here. That's going to close down as a parallelogram, as you can see, and calculating the cross product and then its magnitude gives you the area of this thing. Equals the area of this parallelogram, like so. Yeah. This is super helpful, and again, I'm not going to prove this, but the idea is basically just use base length of the base times height, right? And the height being magnitude times the sine of this angle, of the other angle, of the inside angle. So you can prove it this way. I'm not going to bother. Cross products are a little difficult to handle with determinants and all in proofs. without going too deep into linear algebra, so I'm not going to bother doing this now. And you have to know this geometric fact as well as this formula right here. It's pretty similar to the formula for the cosine and the dot product. And the cross product to get sine and the dot product to get cosine. So let's solve both of these examples. Let's begin with example 19. I want to find the area of the triangle with vertices 102 is P, and there's Q right there, which is 333 sky, and there's R. I don't really care about their relative positions as long as they really do form a triangle. I haven't checked. I copied this from a book, but we want to find this area. Right? So what's the correct way, the cleverest way to do this? Make a parallelogram out of it. Find the area of the whole parallelogram through the magnitude of the cross product. And then divide by 2 to find the area of the triangle. And to find the parallelogram, you need vectors, which you don't quite have yet. So your vector U will be vector PQ. So it's Q minus P. So it will be vector. So I got to do 3, 3, 3 minus 102. So it's 2, 3, 1. And then vector V will be vector PR, which is R minus P. So it will be 7, 5, 8 minus 102. So 7, 5, 8 minus 102 is 6, 5, 6. And then I'm going to do the cross product of these two. It's I, J, K, 2, 3, 1. I'm trying to not make mistakes here, but if I do, I'll trust you to find them. Expansion by the first row one more time. And then this is going to be 3, 1, 5, 6 minus J. This is going to be 2, 1, 6, 6 plus K. And this is going to be 2, 3, 6, 5. So it's I times 3 times 6, 18 minus 5 minus J times 12 minus 6 plus K times 10 minus 18. So this is going to be 13I minus 6J minus 8K. So again, this is the points to stop and possibly check if I've made a mistake. Likely I did make a mistake here, but this is not the answer because the area of the entire parallelogram is the magnitude of this. So it will be then the square root of 13 squared plus negative 6 squared plus negative 8 squared. So it's 169 plus 36 plus 64. So that's 269. I'm going to use my calculator. I actually don't have to. This is just the area of the parallelogram. But we don't want that. We want the area of the triangle, which will be 1/2 the area of the parallelogram, which is 1/2 root 269. Okay, let me just double check that I'm adding and seems fine. And that will be the answer to example 19, the area of the triangle. Okay. That is pretty cool also for the following reason. If the two vectors are parallel, then U cross V is all 0, 0, 0. that follows from property of determinants, and also from the fact that if you have, just imagine the two vectors that you have being parallel, there's no parallelogram. It's like zero area, right? So if you're taking notes, this is something to write down. It's another basic property of cross products, and you can use it as a check too. If I ever ask you, check if a vector is parallel, perpendicular, a pair of vectors, right? These two vectors are parallel, perpendicular, or neither. You can check the perpendicular with the dot product. If it's zero, they're perpendicular. And you can check the parallel with the cross product if you want. And if it's zero, they're parallel, right? So it's sort of more systematic way to do it. Now let me copy this so I can do example 20. So what I just said about vectors being parallel is this small short phrase. So you can use the dot products. And also, obviously, that is because you can look at this formula and see the sine of theta right there. Yeah. So it's the formula I got to remember. And if the vectors are parallel, their angle is, the angle between them is 0, and the sine of 0 equals 0, right? So that's why that all zeros out. Theoretically, you could also use the dot cross product to find the angle between two vectors, but then you're limited to a different range. Okay, 20. 20 is the last one I'll solve. Let me move this out of the way to work on 20. We're to find the volume of a parallelepiped. And so if you have vectors u, v, then you know how to calculate the area of the parallelogram that they define. So this is going to be somehow the cross product. But if you add a vector w here, it's kind of weird, then it will, if you put a copy of w at every of these four corners, right, then this will define a parallelepiped, and this will have a volume. And to calculate the volume of something like this from basic geometry, you know that all you need to do is calculate, multiply the area of the base times the height. But the height is not supposed to be crooked at this angle like this. It's supposed to be straight up, right? And you can use this third vector w to sort of project it on this way. So project w vertically, right? So if you do u cross v is going to point the correct way, but it's the wrong size, right? U cross v may be too long or too short. What's correct is the projection of w onto this guy, right? So that's where the dot product comes in. So use both at once. The volume will be you do u cross v and then dot w. Of course, with absolute values, and then the order doesn't matter. So I'm going to do u cross v dot w like so. So get one vector. So make it super simple. It is what your answer is going to be. I'll take absolute values because I don't really care about worrying whether this thing is positive or negative. So that's all I'm going to do. Do a cross product. I'm going to do that now. I'm going to do u cross v. So u cross v will be I, j, k. So it will be 1, 2, 3, very convenient. -1, 1, 2. I'm sure I'll make mistakes here, so again, I'll count on you to help. This is I, that's 4 minus 3 minus j times 2 minus minus 3 plus k 1 minus minus 2 doing this expansion by rows like I've done before. This is I. This is positive 5 minus 5j. This is 3k. So this is the vector 1, negative 5, 3. And now I take that and do a dot product with w. So this is the dot product of 1, negative 5, 3 dot. And I go back to w to see that's 2, 1, 4. 2, 1, 4. So that's going to be 1 times 2, negative 5 times 1, and then 3 times 4, right? That's going to be 2 minus 5 plus 12. That's going to be, what will that be? 9. Right, 14 minus 5, that would be a 9. So absolute values, just to be safe, but it doesn't matter here because 9 is positive. So the volume of the parallelepiped is 9. Okay, I hope this made sense. This application is pretty important, I think, and knowing how to do the cross product quickly is very, very helpful. But I still say that you should pay attention and check your numbers. I'm sure I've made a mistake here because I've done this too quickly. And as an addendum, I wasn't planning to say this here, but we've already talked about dot products and cross products. So the triple products of u, v, and w is this number here, is the number, and then the order kind of matters. It's u dot v cross w. So I did it in any order that I liked for the volume application, and so for the volume it doesn't really matter. But so the volume is the absolute value of the triple product u dot v cross w. It's really helpful to keep things in that order. So the order for the triple product. So I do think it's kind of important to mention it that right here, but it doesn't really matter that you know this for most classes at the beginning. You can always just remember that you can just do cross and dots of the 3 vectors. Doesn't really matter for sure. Okay.